It's a joint work with Evelina Amatova, and actually have a huge team, a huge cast that I'll mention at the end. I'm going to talk about computational challenges in rich tomography, and we're really at the beginning of several projects in rich tomography. So I'll first tell you what it is, and then let's see what the computational challenges are. So the thing is, typically when you think of tomography, you have sources and detectors in different positions, often a whole array of detectors, but for each source and detector position, you measure one scalar. And then you seek to make an image, typically a three-dimensional image of a scalar, right? So that's kind of old school tomography. So roughly, rich tomography is anything of a kind of high dimensional nature. In particular, I mean that you measure more than a scalar for each source and detector position. I'm thinking typically we're still going along straight lines, but of course there's also tomography problems over curves and surfaces. Here are some kind of examples that we'll go into in greater detail. So for example, you might measure a polarization state of light or particles. So for each source detector, you measure a matrix. You might measure a spectrum. So a spectrum in frequency, energy, whatever, same thing. And that will be a function of one variable for every ray that you measure along, right? If source, detector, you've got a ray, whole function, right? A diffraction pattern, which is a two-dimensional spectrum, really, function of two variables. Or sometimes you get a histogram. So you actually get a measurement of the distribution of something along that ray. So it's surprisingly common, histogram tomography. Yeah, it's a function of one variable. So having gathered all this data, you can be a little bit more ambitious in imaging something more than a scalar image. So one example, or it's like a cluster of examples of diffraction tomography, you have a function of three variables for each voxel, right? So you kind of have like a diffraction pattern in a reciprocal space function for each point in actual space. Less modestly, you might have a vector, a magnetic field, a velocity field, or just an orientation line field without an arrow on it. A tensor matrix, such as a strain that you want to know at each point, or possibly something more like a classification where for each voxel sort of gauge volume, you have the proportion of each of a number of materials in this kind of classification form. So all of those and many other things we call rich tomography. And of course, they vary widely, but they typically have quite a lot of data and quite a lot of unknowns. Most of these methods I mentioned have been done experimentally. They're mostly not particularly mature. In many cases, the measurement apparatus is ahead of both the theory and computation. So they're kind of rich for us as a happy hunting ground for finding interesting mathematical problems. So here's some cartoons of some of the problems I mean. So this one I stole from Marianne Levy's paper, but I think it kind of illustrates a nice idea of diffraction tomography. It's got a mixture of diffraction and tomography. So you've got a little sample there. Typically, you'd fire in a beam of, in this case, X-rays, but it could be neutrons or it could be electrons.
Bill, your slides are all cut off at the bottom. I don't know if it's something you can...
Cut off at the bottom. We did worry about that. How far down does it go?
We can sort of slice this halfway through this analyzer at the bottom.
Yeah, okay. Interesting.
I don't know if you can fix it.
Yeah, and so like, I did wonder whether...
your suggestion is to exit presentation mode.
Exit presentation mode. I have just exited presentation mode.
No, it's too small. Yeah, and then zoom up a bit. Yeah, that certainly looks better.
If I get it just right, then I can.
Fit page. I don't know. Yeah.
I'm not sure if that. Okay, so let's just see. Simon, is the bottom visible now? To make it a bit smaller.
It is.
It is. So I'll just stick with that side, and we'll have to live with the decoration around it. Okay. Sorry about that. Okay, so I can still point as well. So we have a tilt stage, right? And we also raster scan the beam, and that way we do tomography and diffraction. For each ray position, we get a whole diffraction pattern, which is kind of average of the diffraction pattern through the object. We can do this with electrons, and people do. So here's a cartoon of something that might be a single crystal. So each beam going through it, we make a kind of diffraction pattern with spots, and we can raster scan the beam, and we can tilt the sample. And mathematically quite similar, but we'll have to a different thing. I possibly have to zoom in this one a little bit more to see it, but I really have a better picture of this. We fire neutrons through a magnetic field, so like a solenoid, there's a cartoon little coil, and using fancy kind of magnetic devices, we can orient the spin state of the neutron in any of the three directions we like, and then it goes to a magnetic field that changes the spin state, and then we do the reverse. We make a filter that only lets neutrons through with a certain polarization, and then we just measure them like we measure any old neutrons. So we've got a polarization tomography of neutrons for measuring magnetic fields. And yeah, just about works. And this cartoon is just to say kind of neutron tomography. We end up with firing neutrons again on a very long tube, and they have a bit of a race, and the fast ones comes out first. So you're kind of graded by speed. So if you just record the time of arrival, the first ones are the faster ones, and so you know speed's inversely proportional to wavelength. So you get a spectrum for free, and there's all sorts of things you can do about time of flight neutron tomography. So we kind of get a spectrum just by clocking in when the neutrons arrive. So what are the challenges? Well, here are some. I mean, so I think you can draw some general conclusions, and also that you'll see things that come up in rich tomography problems also come up in a lot of other inverse problems. So first of all, we get very large arrays. Multi-dimensional images, for example, SAX tomography, the way I've said it, there's 6-dimensional space. I mean, so each point you have a 3-dimensional function. And so we get very large but sparse matrices, and I'm very glad for Jim's talk, because of course exactly what we do is set up a very large sparse linear system, and often we have to use a regularized solution using the kind of iterative methods that he mentioned actually. So yeah, so I don't have to explain that. This is the sort of thing that we could try. The more you have kind of limited data, the more you need to do regularization. Some problems are actually nonlinear, and when formulated as optimization problems, turn out to be non-convex. And we'll see that the polarized neutron one is kind of archetypal example, but it turns out that even ordinary tomography with large sources and detectors is nonlinear. So nonlinearity pops up a lot anyway, which so Felix's question to James, can we do it nonlinear, right? So spectral and diffraction type problems tend to have low counts per channel. So I said you clock the arrival of a neutron, you measure a diffraction pattern, but in each of those energy bins or pixels, we don't get that many photons or neutrons already. Don't have as many counts. So it tends to not be normally distributed. I mean, if you use classical X-ray and you get big enough dose, normal distribution there is a pretty good approximation, but it tends to not be governed by Gaussian statistics, and it's kind of also rather large errors, so regularization counts for naught. And then finally, the data is often limited. So I mean, in the electron tomography example, we can only tilt it through plus or minus 70. And so it's a kind of limited data problem, and that typically makes it severely opposed. And so you rely more on the regularization. So these are kind of typical challenges. We go into a little bit of a detail of each of these, because given the audience, I think you're probably not familiar with them. And if you're somebody who develops interesting numerical techniques, then you might find some of these interesting problems to play with. So diffraction tomography, this is this first because there's a huge investment in synchrotron facilities to actually measure this data. But let's do it generically first. If you think of diffraction method and just sort of crystallography, you have something that's meant to be spatially uniform in some kind of regular patterning. You look at the diffraction pattern and then you try and do the inverse Fourier transform without the phase to determine the structure of, a molecule or something. And you can do electrons and neutrons, but by contrast, tomography happens on a larger length scale, where you can kind of typically ignore many of those effects. And you really just see how many X-rays, electrons, or neutrons you lose going through each voxel. And the mechanisms by which you lose them could be a variety of physics. But the crucial thing is you typically assume that response is isotropic. So whatever loses those X-rays, it doesn't matter which direction it comes into the voxel. So it's a scalar problem. If you combine the two, essentially it's a kind of two-scale problem that you have, on one side, tomography and a raster scanning and a rotation. On the other hand, for each of those, you have a diffraction pattern, and you kind of assume that, it's something like within the width of the beam, it behaves like a homogeneous thing with a particular diffraction pattern from each direction, but on a macroscopic thing that changes. So it's a two-scale approximation. So just a little bit of mathematical formulation. So it's not just kind of vaporware. So to formulate this mathematically, first of all, think of scalar tomography. You have a scalar function of position. You go along a ray, and the ray is x plus s times xi, where xi is a unit vector, so you're going that way, and x is a starting point. You can think of it as being the source, if you like. And so we get the line integral, and that's our data for every value of line, right? So every starting point and direction. And the point is that f is isotropic, doesn't depend on direction. But in diffraction tomography, we have another vector, q, the reciprocal space, the sort of frequency space vector, and we assume we have a function of position and reciprocal space. So it turns out that typically we measure with a screen perpendicular to our beam. So the thing that we get, the data we get, is the integral of f of x plus s xi along the ray at a q, but the q has to be perpendicular to the ray. So we're kind of only getting the transverse part of it. So we call this a generalized transverse ray transform. And so our data is pairs of, a line, a ray, and a vector you can think of as the coordinate on the screen of the diffraction pattern perpendicular to that. Notice that the space of lines in three-dimensional space is four-dimensional, right? So you need four parameters to describe all the lines in free space. And so typically, if you're doing scalar tomography, you want a function of three variables. You could measure a function of four variables. You don't need to. So typically, you measure a bit less than that. But in this kind of diffraction tomography, it's formally correctly determined. In other words, we want a function f of 6 variables, and we measure a function of 6 variables, which is 4 variables describing a line, and then 2 variables on the diffraction pattern perpendicular to each line, right? So it looks about right, and it turns out it is right, because there's the little theorem et here, which is fairly easy conceptually to prove, that it's got a unique solution if you take complete data. And the proof is really just that if we restrict this to one plane, the plane normal to a vector q, then we can think of f of x comma q as being a scalar function for fixed q on that plane, and then this is just the Radon transform f of something q. So we can do it plane by Radon transform inversion for each value of q if we wanted. And so in principle, you could do it that way. You can measure data on each slice, do a Radon transform, and that gets you 1 point on the reciprocal space. Okay. In practice, you probably don't want to do it that way because, for example, you want to regularize between planes and between frequencies. And you haven't really got enough data to think of it as fully 6-dimensional. So you need some smoothing to happen somewhere. But that's a kind of generic picture of diffraction tomography. Let's look a little bit about SAX. No, SAX with an A. Small angle X-ray scattering tomography, as they call it. So I mean, you can do wide angle perhaps. I mean, but this is particular popular type of methodology that people are developing. So you do it in a synchrotron. You have this elaborate stage, and obviously move the stage in a plane to get the raster scan of the beam. And apparently, so the point is, in a synchrotron, you have a really intense X-ray beam, so you don't need to measure the diffraction pattern for that long, and that makes it feasible to sample this 6-dimensional space. And typically the protocol would be fix the object in an orientation, raster scan it in X and Y, and then move it in steps that step around, samples of points on the sphere. And for each of those, you measure a diffraction pattern with a camera. One thing that's kind of interesting in this is that the length of the Q vector is a length scale, always a 1 over a length. So for each sort of circle in this diffraction pattern, we get we'd be associated with a certain length scale, and you'd be interested in stuff happening at certain length scales. So you might not want all of this picture, right? You might only need certain length scales, and you might regard them as being independent. So here's again pulled from this paper by Levy's, just illustrating that this is the magnitude of 1 over length, and that maybe this at some length scales you may have one preferred direction. There's only really one thing going on, but in some directions you have some more interesting structure. That's what you want to imagine you get out of it, and you get a 6-dimensional image, but you fix one of the length scales, so you get a picture that's got a sphere, a functional sphere everywhere, and then you have to think of some way to analyze that to, for example, extract preferred directions and alignment in, say, a bone or something like that. Okay. Well, how much data? Let's do a data count. I'm not really sure that I'm going to be exascale. I mean, okay, unless you want to go really fast, X of, it also depends how quickly you need to do it. But I mean, it's interesting just to count how many measurements we make and how many unknowns as well. So in an example cited here, the pixel was kind of 2 megapixel sensor, right? You don't need all of that. You can reduce it down, but that's what comes into your hard disk. Typically, a number of projections, there would be 200 or 300 samples around a sphere. And that's kind of an interesting question, how many you need. And then order 60, 70, 80 scan steps each way. Again, you can vary that. And there's a trade-off with speed and accuracy and number of counts that you get for projection and so on. So roughly the data is 410 to the 12 before you did any data reduction. And so typically you probably want to reduce the camera sensor, which is the inner variable in the loop, right? If you could reduce that as you store it, that would probably be the right thing. But in principle, we're solving a system of 410 to the 12 linear equations plus some regularization. So, it is pretty big scale data. So we've got some kind of clever things to do to reduce the operation counts. We don't need to do the whole diffraction pattern. In fact, you can re-bin it into annuli or some combination of the pixels. You can use a model-based approach instead of having a completely general functional sphere, which is kind of a little bit over the top. You can write it as a sum of spherical harmonics and then assume that it's quite smooth. And that's interesting because it changes the theory into something called a transverse ray transform that we already have analytical theory for, and that helps us understand sufficiency of data and maybe cut down the data, and also have at least partly analytical reconstruction algorithms. So that's a consequence of assuming a smoother model. Cut down the projections, but actually there's always going to be a balance here. The number of projections, number of XY scans, the exposure time for each projection are things that you need to work out how to trade off, and you probably can't do that without deciding what it is you're trying to find. So it's kind of model that you can't have a universal rule, I just want a pretty picture, but if you've got a certain amount of time on the machine and you want to find something with a certain accuracy, then you kind of have to design the experiment right. Also, when there are filtered back projection analytical kind of solutions, maybe you can do that as a start, even if you have to apply some regularization later. So that's kind of fairly general thing. Okay, I'm going to go on to polarimetric neutron tomography. So this is, I'm not sure, in tomography, the naming convention varies from what you're trying to image, what you're trying to measure, or something that involves both. Like what's the physics? Anyway, in this case, we measure the polarization state of neutrons, and we're trying to image a magnetic field. So you can sort of polarimetric neutron spin tomography of magnetic fields, if you like. So neutrons, hey, I thought they were billiard balls. They're not. They're like little tops. They have a spin state. Who knew? And while neutrons kind of just have a habit of just barreling through anything you put in their way, which makes them good for tomography of dense stuff, the spin state carries with it. And the spin state is only really disturbed when it goes through a magnetic field. And it makes the spin state change depending on the direction of the magnetic field and the strength and how long it stays in it. And so we can use that to measure. The other thing, it's kind of an advantage that when you make neutrons, they come out of your source at lots of different speeds. The distribution of speeds is more or less known. You make the neutrons, by the way, by smashing protons into something, which is also great fun. But the neutrons then go down a very long tube. That's to make sure they're collimated, right? So you lose any naughty ones that go out in different directions. But also they have a race. The first to come out the end of the tube are the fast ones. And so because neutrons, the speed's infinitely proportional to the wavelength, they act like waves in that way, you automatically get a spectrum just by time gating where you measure. And of course, the faster ones have spent less time in the magnetic field, so the polarization state hasn't changed so much, and the slower ones change quite a lot as they go through. Kind of use that as an advantage. So the governing equation is kind of neat. Sigma is the name for the spin vector, and you go along array x plus s size as normal. But what happens, instead of a kind of Beer-Lambert law, we have this system of differential equations, which is the magnetic field vector B cross sigma is proportional to the rate of change of sigma. So the cross product varies. So the sigma varies with the cross product with B. And underneath, we've got the velocity just as a parameter. As I say, the longer it spends in the magnetic field, the more it changes, right? So this is interesting because you can't just take the log in this case to solve the ODE like you can in the scalar case. And so we actually have an ordinary differential equation, and you think of the input to the output map. In other words, we put in some spin states, well, 3 in all directions, and we measure what comes out. We actually measure an orthogonal matrix that tells you how the spin state has rotated going through the magnetic field along that ray. So the measurements of matrix immediately tells you it has to be nonlinear, right? It's not even in a vector space, so it can't be linear. But we measure basically orthogonal matrices, and this makes it kind of interesting because if you only looked at one ray, you couldn't tell if it had wrapped around once or 100 times round by the time it gets out. There is a uniqueness theory that says if you measure from all directions, or actually just all directions in a plane, then there is a unique solution, but it's non-constructive. And in practice, it makes it a difficult nonlinear problem because of this, what you might think of as a phase wrapping problem. So it can be done plane by plane independently. I mean, of course, until you say, well, the magnetic field is smooth, so I should regularize it between the planes. But the point is, the theory works for uniqueness of solution plane by plane, for B with all three components, but going along lines. So it's kind of unusual in that way. If you don't take enough projections, you get a non-unique solution. And if you look at, just sort of one part of the data, you will see it oscillate as the spin state goes around. And so the objective function is non-convex, and we run the risk of falling into local minima if we're not careful. So even though the theory guarantees a unique solution for complete data. We also have this range of speeds, which we kind of have incidentally. We just don't, they come out with all sorts of speeds, and then they have a race. So we can just use fast neutrons and we can use slow neutrons. So the point is kind of interesting that we can make a linear approximation to this for small magnetic fields, or of course, large velocities. It's the same thing. And so you can, wherever your magnetic field, you can use the fast neutrons to use something where the linear approximation works well, but you don't have that many fast neutrons, so the data's not that accurate. So there's a kind of hierarchy where if you want to use all the neutrons, then you've got to embrace the nonlinearity, but the faster ones give you something that's closer to the linear approximation working. So I think there's a kind of whole range of interesting things we could do in that, but it's been suggested, and so it's tried with simulations at least, that we use Bayesian Mcmc methods, because we find that we have to use stochastic optimization anyway to not get trapped in local minima. So we may as well do something that has some kind of theoretical guarantees. And also because of the low number of counts for each velocity, we'd like to do uncertainty quantification for that well. So, I mean, of course, as soon as we're doing MCMC on a three-dimensional inverse problem, we have a huge computational challenge just to solve all the forward problems. Okay, so moving on, I'm a little bit aware of the time. I think we're running about 3 minutes late, and I thought maybe I could make up the time if I speak very fast, but let's see how it goes. So I'm going to talk now about time of flight neutron spectroscopy. Now, I think that might go off Simon's screen, so let's make it a little small. So this is just doing, if you like, when it's not fancy polarized, but we still have the same neutron source that gives us a range of speeds. And we clock the neutrons coming in for each pixel. And I mean, so the interesting thing is that we look at stuff that's mainly, to some extent, crystalline, and even if it's polycrystalline, like a metal, that each spectrum tends to have a kind of rather interesting structure like this. What happens is a lot of the neutrons that we lose in a crystal are lost by Bragg diffraction. Otherwise, they go off somewhere else, and we're nowhere near our camera, and we don't detect them. So that just looks like lost neutrons. But the point is, the Bragg angle is related to this spacing of the planes of atoms in our crystal. And there comes a point where, what can I say? You have 2D sine theta is meant to be a multiple of lambda. There comes a point where that would mean sine would be bigger than 1, and there is no Bragg diffraction. So it's a kind of a certain speed of wavelength of neutrons beyond which then suddenly not being Bragg diffracted, and then suddenly the number of neutrons getting through jumps up, and we call that a Bragg edge. So we get one for each of the crystallographic planes, and ideally it would look like this. Of course, it doesn't look like that. It looks much more complicated. But we can use this either to characterize materials or something about the structure of the crystals present, or if it's nicely uniform, we can measure if this Bragg edge, which corresponds to a spacing of electron planes, if the sample is strained, then the strain in the direction normal to the plane of electrons will stretch that distance, and so it will change the wavelength at which you get the Bragg edge. Now, of course, this is a summary of what happens all the way along one beam. So if we have different strains, instead of being one edge that's moved, we'll get like, a staircase. In fact, we get a cumulative histogram of strain from that. So that's, I mean, because it doesn't look, it's not nearly as ideal in this, and the devil is in the detail of pulling that out. So actually that's a fitting function to a one Bragg edge. So this is all the processing that we're going to do for each ray, right? So we're going to do this tomographically to get all the 6 components of strain, and then we have a big calculation to do. So we've done some preliminary things on one projection, and we've also done some reconstructions of. Sorry, yes, I'm just aware of time. I'm just going ahead slightly. Okay, so let's do our count of data. It's not too bad. The detector that we have is a 512 by 512, and but we get thousands of spectral points, time of flight bins, because that's just a time resolution. We took 120 projections for one of the experiments that we did. It's really a matter of time versus number of projections versus time averaging for each projection. So the total data on this is something like 10 to the 11. Then it depends how we're going to reconstruct it, assuming what about the spectrum. We actually used golden ratio sampling, which we thought was very, very clever, because we sample the angle at a ratio of golden ratio times 180 degrees. And what that actually does in practice is just kind of go around filling in the gaps as you go. And this is ideal if you're going to be interrupted and thrown off the machine at any time. So it's like the best thing to do if you don't know when you're going to have to stop. And then when we realize the reality of it, the thing does break down regularly, and you don't know if it's going to come back on. So actually, it's a really good strategy to do that. What we didn't think about is we don't really kind of have a rule for how long we should average in each projection, because, if you only had one projection, really, really accurate, you really wouldn't know very much at all. And if you only had one neutron for each projection, you'd also know nothing. So there's got to be a sweet spot in experimental design for this. It's very slow. I mean, you book the machine for a few days to do this sort of experiment. So the neutron source spits out a variation energies that's determined by lots of physics and the way it was designed. So we can know that spectrum, but we don't choose it. And then within that, you think it might be a Poisson process, because it's kind of an arrival of neutrons. Actually, it's quite a lot more complicated than that. So it's not Gaussian or even Poisson noise. And so, we're in the statistical reconstruction kind of framework. So we could try and reconstruct each energy bin just as a scalar image, but it would be a very noisy image. And then, of course, the kind of moral is we should couple it using the spectral variable, or decompose it into, say, a library of a number of materials in which we've got components. Or if we're doing strain tomography, then we want to fit this curve to extract the components of the strain. So here's a reconstruction of some samples which were different metallic powders, just as a test thing. And maybe it's worth just, spectra really look like this, and so kind of very, very noisy. Well, I need to move on to electron. That's a lightning tour of all the different types of rich tomography that we're involved in at the moment. Electron tomography there's kind of 2 flavors of electron tomography, actually. One is the cryo-EM that you see in biology. So if you've tried to help out with the coronavirus imaging, typically they have a frozen sample, and they have a parallel beam electron tomography system with a limited tilt angle. So up to some details, it's it's parallel beam tomography with limited angle data. In practice, actually the sample degrades as you bombard it with electrons, and there's all kinds of other modeling problems, but it is essentially parallel beam tomography. For material science, they do something rather different. They tend to raster scan a single beam, and then they look at well, they don't necessarily look at the diffraction pattern, but from the diffraction pattern, they just pick part of it, like an annular average. And that's because the straight through beam is way too variable with lots of strange effects they can't easily model. So they actually do some kind of diffraction tomography anyway, using scanning transmission electron microscopy. And they're doing what's called a dark field. In other words, they ignore the middle of the diffraction pattern. The tilt stage is still limited to plus or minus 70, and that's largely because they make a thin sample and it can't go through it if you tip it on end, because the electrons just don't go through it. But apart from that, we can think of it as diffraction tomography. So we can kind of apply the same mathematical ideas, apart from, quite a lot of interesting and difficult kind of modeling of it, but also the fact that they've always got limited angle. One of the motivational problems we're looking at is measuring the strain in a single crystal of silicon. And the idea of that is electronics. As they make electronics smaller, the junction on top of their crystal of silicon varies with the strain. In other words, the electron density and hence the properties of that junction vary with the strain. And so they want a way to measure the strain. So that's at least, there's lots of other reasons to do this type of tomography. So here's our cartoon again. I suppose you can use several beams at once, but the point is that you'd raster scan this beam, tilt the sample plus or minus 70, and you get these diffraction spots. So what do these diffraction spots mean? Well, if it was a pure, infinite, homogeneous crystal, then you just get a regular array of dots. The dots are slightly blurred by the physics, the optics of the system, but also the crystal isn't uniform as you go through it all the way along the ray path. So it might have defects, for example, but in particular, if it's strained, then that changes the crystallographic spacing. And so we think that along the ray, we have different strains. The strains will spread out the dots in my diffraction pattern, making blurred dots. In fact, if you look at one of those dots, it basically tells you the distribution of the positions of the atoms along that ray path, right? At least in the direction perpendicular to the plane. So it's kind of even fancier data than we had before, but it contains a kind of distribution of strain data perpendicular to the ray along the ray path. How much data? Well, look, they've only done feasibility studies, but the sorts of thing they're talking about is they have a screen with 1,000 by 1,000 pixels, which typically each pixel doesn't really have enough electrons in, so they rebin them to something more like 100 by 100. They raster scan 50 beam positions. Imagine, actually, this is a much smaller sample. It's kind of tiny crystal of silicon. So they might be doing 10 to the 9 measurements with 40 projections at different angles. But this is early days. It's just beginning to actually do this experimentally. It is limited angle, so we'd have limited angle artifacts, right? If we did analytical methods, but of course we don't. We do numerical methods, the sort of thing that James mentioned in the first talk, and we need that because we've got missing projection angles. And the regularization plays a much bigger role in that sort of problem. And you have to be careful that you can extract the information you want reliably. And as a histogram, though, if we, obviously we could just sort of take the center of mass somehow, or some weighted center of each of those diffraction spots and turn it into a linear problem, right? But actually that's throwing away a lot of the data. And if we said, well, we've got a histogram, we've got a distribution, and of course that's nonlinear because it It says go along the way and count how many displacement vectors you've got in each kind of bin. So that's immediately a nonlinear problem to use all the data, which is another feature. So you can have a kind of cheaper linear problem, but it's either amalgamated or discarded some of the data. Okay, I do want to leave some time for questions, and also we're running a little bit behind. So you can go to the conclusions. I mean, it's conclusions and discussion. I mean, I kind of have to admit that we vary from some of these experiments we've done, some other people have done, and we're about to do them. Some we've got quite a long lead-up time to do. But, you know, all of these are live enough that we will get experimental data, and we will get reconstruction results. But they're at sufficiently preliminary stage that it's still very worth thinking about what sort of methods we would use when we get large-scale real data. And we were talking just before the meeting that somehow the weather, people like, we'll see sort of working Chris Budd's talk, they always had kind of huge amounts of data on several different time and length scales. And of course, also in seismic work that we'll hear about, they're also used to dealing with very large amounts of data. But for tomography, you know, somehow the scale of these problems is new to them. And, you know, they have to start thinking about not just that they have to hire mathematicians, you know, our young postdocs to work out clever ways to do it, but also they're also going to need more efficient computation and to think carefully about parallelism. So rich tomography generally results in a huge potential increase just going to higher dimensional problems. And this is without saying also that there's a kind of Moore's law in the camera detectors. There's an increase in speed, as for example, they get more powerful synchrotron sources, they can go faster. And so you add a time dimension as well. So, you know, really, if you don't do something, you will simply drown in this ocean of data. But using theoretical insights, we can often cut down the data size without reducing relevant information. So an analytical understanding of sufficiency of data, perhaps sufficiency of data with some constraints on the problem, allows us perhaps to just measure a smaller data set that still contains the same information. So be smarter about what you measure or what you store or what stage you aggregate the data into a smaller data set using the theory that you know for that particular problem. So some problems have a natural product structure. For example, polarimetric neutron tomography splits into planes. We could farm them out, each plane to be done separately, right? But actually, the magnetic fields are typically very smooth. I mean, so we're thinking of magnetic fields within a device or something might have some discontinuities at boundaries that we know, but we can assume quite a lot of smoothness. And so we do have to couple between the planes to reinforce that smoothness. That breaks the product structure. And that's kind of an interesting feature that you know, in a lot of ways, so for example, spectrally, we could split the reciprocal length scales in our diffraction pattern, but of course they are actually coupled. So, you know, you could maybe couple them on some kind of neighborhood in reciprocal space, but there's a compromise between the coupling of the linear system and the extent to which you're actually enforcing known a priori information, thus making it smoother, and I mean also therefore making it better posed and the iterative algorithms converging faster. So I think there isn't one size fits all. These are things you have to ask for each of the problems that you come across, but there will be commonalities. So regularization breaks coupling. Model-based approaches to a priori information systematically decreases the number of unknowns. For example, assuming a spherical harmonic expansion seems a perfectly reasonable thing to do for SACS tomography. But I mean, you know, it's a question of finding a model-based approach that includes the information that you want and the a priori information is kind of more or less true. I think increasingly we're going into a Bayesian world, and as soon as we have nonlinearity, especially resulting in non-convex optimization, but also when we have low count data and limited data, the UQ, the uncertainty quantification, becomes more important, and it's not just good enough to get bigger computers. And fortunately, the Bayesian people are working on this. There's lots of nice Bayesian methods that will work in high dimensional spaces, but I think we're increasingly going to see that as we just conquer the computational challenges of being able to solve the forward problem efficiently and quickly, because any Bayesian type method will have a lot of forward problem evaluations. So I'm coming to roughly a conclusion. We'd like to thank all our wonderful experimentalists who patiently explain how their experiments are meant to work, and we're slowly understanding what the underlying errors are. EPSRC has funded us for a very jolly rich tomography grant across Manchester, Cambridge and Oxford, which has just started. Evelyn is funded also by the Journal Agency, and Advert in 2023, probably the first half of 2023, we've got a program on rich and nonlinear tomography in the Isaac Newton Institute, where many of these discussions will continue, having made some progress and possibly also got stuck somewhere. Okay, that's it for me. I think it's over to questions.